Thank you, Mark, for the kind introduction. Thank you for coming to see what I have to say. It goes without saying that because of my experiences at the University of Pennsylvania, I don't think I'd be here today. And I'm very grateful for the education that I received here. And I worked in the GRASP lab when it was in 2 different locations. And through those experiences, I'm just very, very lucky. What's interesting is when I come back to Penn, seeing the new faces, the new people who are here. And there's some wonderful colleagues that I've had. So whenever I come back to the University of Pennsylvania, it's both a homecoming and an opportunity to see some new people. So thank you again for having me. My research group over the last 15 or so years have done a variety, actually 19 years, has done a variety of things. I think we're famous for these snake robots. We're getting into, obviously, we've done some medical robotics work. And recently, some manufacturing as well as issues in modularity, which Mark really set me on that pace. What I'm proud of with the work that we're doing in all these areas is that we're actually working with some practitioners. So here, for the snake robots, last year we went to Mexico City and by the invitation of the Mexican Red Cross and helped clear buildings looking for potential survivors. In terms of medical work, my students and I and my collaborators, we formed a company called Medrobotics that makes this medical snake robot. Here, I should also acknowledge I have another startup making AGVs and technologies to support AGVs. And then there's this other company that makes modular systems. Hebi is the Japanese word for snake, so Hebi Robotics. And then finally, as Mark pointed out, I was the co-PI in putting together the Advanced Robotics for Manufacturing Institute. It's one of 14 manufacturing institutes that President Obama installed. And this one, it's about a $250 million over 5-year endeavor. The thing is, you don't talk to academics for the applications. You talk to us because of the basic science that we develop, and we use the applications to stress test our ideas and to make sure that we didn't make something up. So the areas that my group works on are listed here. We've made some nice mechanisms. We figure out where those mechanisms should go. That's path planning. We do a lot of novel locomotion. And finally, we like to close the loop. We have to figure out what's going on, where are we, and so forth. So I'm hoping today that I'll have time to go through some of these areas. Let's start with the snake robots, locomotion for snake robots. So like any good scientist, engineer, you start with Lagrange's equations. And if you know what your inputs are, simulating what's going to happen really isn't that hard a problem. It's the reverse. Given you want to go in a certain direction, what should your inputs be? And this can be a hard problem, for all the reasons that second order, nonlinearities, et cetera. And if you make some assumptions, one of them is really, the top one is conservation of momentum. And the other one is, if I'm standing here, this is my left. And if I'm standing here, this is still my left. If you make those 2 assumptions, you can end up with a very simple first order relationship. And what I like about this is that we've been able to reduce a complicated problem down to something that's tractable, something you can play with. Now, for the roboticists here, I think this expression looks a little bit familiar. If you notice, there's an alpha dot on one side, there's a body velocity on the other side, so it's like a Jacobian. Remember a relationship between our kinematics class. And in our case here, it's just a little bit different. It really isn't a Jacobian, but what you have on the right are these shape spaces, these shape velocities, and on the left, you have your position spaces. So what we want to do is figure out how can we coordinate our internal shape degrees of freedom in order to propel a displacement in our space. So if you kind of look at this expression a little more carefully, we can plot each row of that Jacobian if you want. It creates a vector field. And now your inputs are, if you want to go, say, in the x direction, some maximal way, you flow. Oh, this pointer sucks. But it's connected. I don't know if I want to. OK, it's kind of a bimanual manipulation problem. So if you flow with the vector field, you'll get maximal displacement. And if you go orthogonal, you'll get no displacement, because dot product is 0. What we want to do is describe gates. A gate is a cyclic motion in your shape space. So as I'm walking, I'm cycling through my ankles, my knees. That's my shape space. And if we have this nice closed loop, we can figure out how far we displace. The thing is, this kind of analysis, you take the dot product of the tangent of that circle with all the vectors, you can figure out how far you go. That can be a little bit of a pain to do. So what we do instead is we take recourse to Stokes Theorem. Remember Stokes Theorem, path integral in a vector field is the same as the volume contained, same as the curl inside of that path. If you do that, now you can just look at this space here. So this is a contour plot of the same picture up there. And just by drawing circles with your own intuition, you can now design gates for systems that in the past have been hard to intuit. So that's nice, but what about higher degrees of freedom? So one of the things we did, and this is a recent student, Tony Deere, I forgot his picture, he's now a faculty at Columbia. One of the things we did is we kind of figured out, if you make some assumptions about how some of the joints are passive, you can coordinate one or two of the internal degrees of freedom, and then from there you can plan a path by properly synchronizing the phase relationships between the first degree of freedom and then how the other ones evolve to sort of steer or go wherever you want. The thing is, this is a little bit hard. So what we do instead is we take recourse to what's called basis functions. Okay, so now if we're looking at this three-link robot again, this three-link robot, here's one joint, here's another joint. Think of a Dirac delta function is a basis vector for that joint. So what we're doing here is we're plotting something in our curvature space, and a Dirac delta is like infinite curvature at your joint. And this is something how, one way to think about conventional linked mechanisms. But instead of having these Dirac delta functions, what we can do instead is we can have other kinds of bases. So one of them would be sines and cosines. Now it turns out that Professor Hirose a long time ago thought of this idea, but didn't realize he was working in a curvature basis function space. He invented this thing called the Serpentine Curve. But now, instead of trying to figure out how to coordinate just 1 or 2 degrees of freedom, we couple them together with this basis function, and now we have this new shape space where 2 parameters, one for the sine, one for the cosine, denotes what all the possible combinations of shapes that you can have. And then once again, wrong button. And once again, by drawing a loop in this space and then taking the volume in it, you can now plan a path for this multi-degree of freedom system. So what I find exciting about this is that you have as many degrees of freedom as you want, but you're still using 2 basis functions, 2 joint angles, if you will, in order to coordinate this kind of motion. So one of the things I'm hoping is that we can look at more complicated systems, and if we can reduce them down to just 2 basis functions, then we have an opportunity to analyze them, plan paths for them, and perhaps learn something more about these systems because it's easy to think about things in 2 dimensions. Now, one of the problems with this approach is that we have these idealized assumptions. We have these so-called non-holonomic constraints. And those are nice, but we want to be able to have these things work in a real world. And here's where my collaboration with Dan Goldman sort of starts off. So this is a sandfish. It's a little animal. It kind of swims in the sand. But what's interesting here is that this mechanism, this animal, is interacting with a granular medium. And what we want to do is, can we come up with that relationship, that Jacobian-like relationship, but for a granular media? And that's something which in the past has been a little bit hard to do. So what we did is we created this robot here. It has 3 links again, and it's in these yellow BBs. And what we were able to do, and this is where the universe was really kind to us, we perturbed for every pair of alphas, for every shape variable, we perturb them, we inject a little bit of velocity into each of these joint angles. So at a given joint angle, we try one velocity, we try a bigger velocity, and so forth. And after trying this for every combination of velocities and joint angles, we noticed that this linear relationship between our shape variables and our body variables just magically emerges. Okay? This is dumb luck. This is the universe being nice to us. And now what we're able to do is use that linear relationship to derive that Jacobian-like relationship. It's called a connection. And then from there, we can design our these 2-dimensional height functions, and we can design our gates. So in the past, when people, believe it or not, people studied this system, actually Nobel laureates have studied this system, the best they can figure out is this was the closest to an optimal system, and that's after days and days of simulations. But with us, within a second, you can see this butterfly shape gives us an optimal step forward. Here what we're doing is the function you're seeing there, remember that Jacobian has 3 rows, x, y, theta. We're plotting the orientation here, and now we're able to get this robot to orient inside of a granular media. So making it go forward, you needed lots of computation. Figuring out how to rotate in place, no one was able to figure out with the best computation because it was just intractable. But for us, we were able to pick it off, and there we go. So what we can do now is we can recycle this idea of basis functions and do the same thing for the snake robot. So here we have this bed of blue BBs, and we're actuating every possible combination of our basis functions with velocities of these basis functions. And we build up this connection. And then from there, we take the curl and we design our gates, and off we go. We now have this mechanism, high degree of freedom, 60 degree of freedom system, rotating in this nice bed of BBs. So a question to ask is, we got it to work, but how good or how accurate are we really predicting these motions? So again, in collaboration with Dan Goldman's group of some of his students, some of my students, we were able to do some empirical calculations where, again, this is the shape, this is the function that emerges for this mechanism going forward. And then we plot it against the experiments, and you can see that not only does this thing go in the right direction, the theory predicts how much it'll go in that direction. And of course, where the optimum displacement appears from the theory agrees with the experiment. So that's nice, but again, we have this contact issue. Before, we were assuming that this mechanism was constantly making contact with the environment. But the reality is, for, say, mechanisms like these sidewinders, they're making and breaking contact with the environment. In fact, the sidewinder, you can view it as having a vertical wave and a horizontal wave going through the body at any given time. And you could recycle the same ideas that we had, but if you then have two shape basis functions for each of these waves, you're living in a four-dimensional space. And at that point, the analysis, again, becomes a little bit intractable. But what my grad student, Choset, what he figured out is that there's a natural way in which we can couple the vertical and horizontal waves, and that coupling pretty much came from understanding just how the mechanism makes and breaks contact with the environment. So now we're back to having a pair of basis functions, but each basis function encodes in it not only the shape, but also the contact state that part of the mechanism is going to make. So here's some analysis where we use some RFTs as this first principles derivation, and we see how our prediction agrees with the RFT. And that's nice, because in theory, everything works. But what we did is we compared this to actual real snakes, as well as the robot. So for the real snakes, by observing what the wave number on those snakes are, from that you back out what the base, you take a guess as what the basis functions are. And it's pretty cool that this geometry actually seems to resemble what the optimal, amplitude as well as displacement that each of these animals are taking. And again, here we're guessing it's two waves, and here we're guessing it's one wave. I should also note that the amplitude of the wave has a linear relationship with the track angle, and after about 30 degrees, that relationship breaks down. So that's why things work well from here over. Over here, we did the same thing with the snake robot, empirically generated the connection, and you can see again with our empirical derivation versus experiments that we ran, everything seems to agree. So I'm pretty excited that with these two basis functions, we're now able to make some analysis. This is pretty cool. If you remember from the coupling between the horizontal and vertical waves, there's this phase offset. And what we were able to do is we can plot a bunch of these functions here, and we're varying the phase offset. So you can see here at 0 degrees is red, and over here at 180 degrees there's black. So in that case, what was a mountain became a valley. So the way sidewinders change directions is as they're moving along, it's not like you can go backwards, put your car in reverse and then have the engine go backwards. It's not like you can have your joint angles go in a reverse direction. With the snake, the waves are always going head to tail, head to tail. Some go tail to head, but they don't change directions. The way and this is something that we discovered, the way that a sidewinder changes directions is that its vertical wave experiences a 180-degree phase shift. So in other words, whatever up becomes down on that vertical wave, and because of that transition, the animal starts to go in the reverse direction. It's sort of similar to how ultrasonic motors work. But you can see that's the case here with these height functions, because if you draw a loop around this middle, you're going forward, and then if you induce this 180-degree phase shift, then all of a sudden that same loop is going backwards. And we were able to corroborate that. So here's a pointer to future work that I'd like to do. We have all these basic behaviors that we have. We want to be able to tie them together to do some real path planning. And right now, this is a canned demo. We hand-wired things. But what I want to do is borrow some ideas or steal, plagiarize, whatever you want to use from Dan Kotichek from sequential composition and create these funnels or these funnels in the workspace and then defer the computation on the full configuration space to on the fly, again, using that Jacobian-like connection matrix. And how to do that yet, we don't know, but maybe. I want to acknowledge that we looked at some other systems. This is a mud skipper. It's a kind of fish that can breathe air. I don't get it. But it's representative of the first fish that came out of the ocean and eventually evolved into amphibians. And one of the things we were able to do was, again, come up with a connection vector field, one of these vector fields for this mechanism after assuming some 2-degree of freedom approach. And then we were able to show that the coordination of the tail and the fins matters a lot when you're going up a hill. So, I was talking with my colleagues about this, and he just says, well, I guess everything to you looks like a snake, because what it's showing is that in order for a fish to have left the sea, it had to be elongated. And that's what our analysis shows. So at the very, very least, if we were to build a robot version of this, we would have to have an elongated tail. We recently started moving on to legged systems. And here are these back-bending quadrupeds. And once again, for this, if you make some assumptions as to how they make and break contact with the environment, we're once again able to get these functions, one for the X and another one for orientation. And you can see we're making this robot turn in place from this analysis. But what we were able to do also is look at some videos of real geckos. And what we're able to, and you can see that our predicted optimal displacement of coordinating the legs and the back almost agrees with what the we're assuming what the animal is doing is optimal, but it seems to agree with what the animal is doing. That's the red versus blue in the top there. And from this, we have, we have some thoughts about extending this to multi-leg systems. All these videos aren't going, so I'll just tell you its future work and move on from there. So let's change subjects. Let's talk about minimally invasive surgery, okay? I think, I'm just curious, how many of you had minimally invasive surgery? You don't have to tell me. At least one of you has taken me to minimally invasive surgery. But the idea is you want to have, well, you don't want to have minimally invasive surgery. First, let's just start there. But if you have to have surgery, you want to do it minimally invasively because it hurts less. It's actually cheaper. And what I'm looking toward now is trying to see how we can have minimally invasive surgery help disseminate medical care and get it out of centers of medical excellence. The thing with conventional minimally invasive surgical devices is that you're limited to either rigid laparoscopes, so they can only access that which is in line of sight from where the incision is, or you have these flexible endoscopes. They're flexible, but they buckle easily, so you're only limited to the luminal tracts, like your intestines, for example. What we want to have is this, or what we have is this surgical snake robot that inherits the best of both worlds. It's both rigid and linear, and because of that, you're now able to navigate the cavities, because you can steer your laparoscope wherever you want, or you can ensure your endoscope will get wherever you desire. So here, this is my clinical collaborator, Marco Zanatti. He used to be at Pitt. He's now at Harvard. We're doing minimally invasive surgery on this pig. It's about a 40-kilogram pig. And the idea is we want to do this procedure where we get to the left atrial appendage. By the way, this is not minimally invasive surgery. We just cut it open so you can see what's going on. But you can tell that the snake robot, it's sailing between the pericardium and the beating heart. Your pericardium is transparent. So here we're seeing through the pericardium to see the snake robot go. So this is nice, but one of the things that Marco and I were able to do was we were able to take this technology and really kick it over the fence with the help of one of the economic development organizations in Pittsburgh, and we started a company called Medrobotics. Originally it was called Cardio Robotics, but now it's Medrobotics. And in this experience, look at the difference of the robots. Here I have a Microsoft joystick and this wood holding the robot up. Look at this sexy robot there. Isn't it nice? So, I'm proud to say that, a few years ago now, we did our first in-human operation. And what you see here is a live fluoroscopy of the snake robot wrapping around this woman's heart. This is the view from the catheter, from the vantage point of the robot. So now you see that white. This is white because your lungs are white, except if you smoke, and the pericardium is transparent. So you're looking through the pericardium up into the lungs. And for this procedure, it was a 4.5-hour procedure. And I'm proud to say that the woman who had this, she went home from the hospital the next day. And she didn't have this sternotomy, this full cut. If she'd had that sternotomy, she would have been in the hospital for 14 days, okay? What's funny is after the operation, I flew back to New York, I called up Marco, and I said, hey, it was a success. And the first thing he asked me was, did the patient live? And I just couldn't get that. I was like, of course the patient lived. I wouldn't be excited for one thing, but these aren't experiments. I mean, you really have to go through a lot of safety protocols. The next question he asked was, did the patient experience any hemodynamic compromise? And for me to explain to you what happened, my heart is suffering more than what her heart suffered having my robot go around it. So it was pretty nice. We got the EU mark, and of course we cleared the FDA. We're the first medical robot to clear the FDA with the term robot in its indication. If you look at Intuitive Surgical, the word robot won't appear. And there's been all sorts of cool successes. This was last year. An Australian surgeon removed a 6-centimeter tumor out of someone's neck. 6 centimeters, not millimeters. So imagine the quality of life change. The thing is, let's go back to this first in human procedure. Here's Petter. He's driving this joystick, and he's looking across the table. And on the other side of the table are these 6 monitors. And with these 6 pieces of information, he's trying to figure out what's going on? What's the situation? What's the situational awareness? So he has different modalities, and in his mind's eye, he has to fuse it together. And this is what doctors do today. What we want to do is almost make it like a game, a video game, or something like the movie The Matrix. And here we have a heart that was CT'd the night before. We have some fiducials that we're helping navigate. And we can now, in real time, create this image, which is nice. In fact, the contribution that's here is that it's a straightforward common filter, except that we're doing something a little clever about the constraints, because obviously the snake robot can't go into the heart. And if you know that, you can project your estimate distribution onto the constraint, renormalize, and then you have a better estimate. The thing about this particular experiment is that we made a strong assumption as to where we knew the base of the robot is. We had low uncertainty. And in practice, again, that's not necessarily realistic. So the kind of problem that we're thinking about now is registration when you have high uncertainty. How can we find a correspondence between what I'll call this CAD model, this preoperative model, and then some live operation? What's the transformation, the rotation and translation? So to do this, it's a highly nonlinear problem, and we kind of backed into this. We ended up using something called a dual quaternion. So in the robotics world, quaternions are a way to measure rotation. It's a 4-vector, it's a 4 number. A dual quaternion is a pair of quaternions, just like a complex number is a pair of scalars where I squared equals -1. Dual quaternion is a pair of quaternions, Q1 plus epsilon Q2, where epsilon has the property epsilon squared equals 0. It's worth noting that we derived a principled way with which we were able to decouple rotation and translation with this dual quaternion framework. We actually thought we were the first to have done that, and we looked real hard, but it turns out Marcel Liber in the early 80s did it too, but his paper was typed up on a typewriter, and then it was scanned in, so we couldn't search for it. But that's okay. So now that we have this decoupling between the rotation and the translation, we can use a quaternion to represent rotation just by itself, and that gives rise to this linear measurement model. In fact, now that we have this ability to have our h of q and our uncertainty come out in a closed form solution, we're no longer resorting to linearizations. In other words, what we have is something that truly is linear. And that's what our measurement model gives us. With this in place, you can then invoke some sort of Bayes filtering approach. But you have this issue of the prior. Now, you can't assume with quaternions or dual quaternions that your prior fits inside of a Gaussian distribution for a couple of reasons. One is, with a quaternion Q equals minus Q, so you have sort of two things. And then finally, you have this unit magnitude constraint you have to deal with. So what we did instead is we, Arun, my student, he just found, or I didn't know about it, this Bingham distribution. And essentially, it's a two-bumped Gaussian on a circle or a sphere or a hypersphere and so forth. So now we can represent this as a Bingham distribution. And it turns out that when you have a zero mean Gaussian with a unit normal quaternions, that Gaussian also becomes a Bingham distribution. So the product of these Bingham distributions is a Bingham distribution. So we have a linear filter, but instead of using Gaussians, it's a Bingham distribution. And then you can get your estimate from the most likely, from the most likely estimate that's commonly used with the Bingham distribution. So we went to town with this, solving a whole bunch of registration problems. But the one I want to talk about is this compliance registration, where we're using force information palpation, which is important for medical systems. So I just want to take a quick sidestep to note that my research group, we spent quite a bit of time developing all sorts of force sensors that have incredible variability. Whoops, my bad. You can see over here, he was hammering this as well as rubbing a feather against that force sensor. And it's something that we're pretty proud of. And of course, we're going to put it on our robot feet. And then here's a version of that force sensor for the Da Vinci medical robot. So the problem we'll talk about now is it's a simultaneous compliance and registration problem. I know what you're thinking. It's SCAR, which is not good for medical robotics, but neither is the word killer application. So if you have your registration, figuring out the compliance model really isn't that hard. If you have your compliance model and some geometric understanding, figuring out the registration also isn't hard. It's this chicken and egg problem that we want to solve. And the way we do it is, just looking at this picture, this is a ground truth of what's going on, and we have this silicon thing where there's an artery inside of it. And as we're moving through, we're palpating that artery. This is what the ground truth is, so it doesn't change. You can see the pokes that we're doing. And then over here, what's happening is as we palpate, we do have some geometric information in the CAD model. Our registration, our geometric registration, pops up really quickly. And then as we continue, we're also getting our stiffness map. So we're able to get a registration for the stiffness map and the stiffness map at the same time. The only thing to note here is figuring out the next place to palpate. What we do for that is we represent the stiffness map as a Gaussian process, and then we use the Gaussian process. There's all sorts of measures you can use. The one I happen to like is expected information to figure out where's the next best place to poke. So there's some Bayesian optimization going on here. And this work we're now using to go look for bad guys and gold and other things that people have to look for. In this video here, we're sort of tying the whole thing together. It's this left and right. This is from the Da Vinci kit again. And we're seeing how the surgeon selects, in this case, it's the prostate, and then automatically we segment the image. And now what we're going to do is the robot's going to come down and it's going to start palpating with the force sensor that we developed. And after a couple of pushes, it'll have this 3D model that also encodes the compliance information. So not only can you whiz around and look at it at any possible angle, if you care to interrogate this model, you'll know how hard and soft things are. So this notion of compliance, I'm going to change subjects again. This notion of compliance is something that runs through not only our estimation work, but also our controls work. I think, it's funny, we have these adept, or this is orange is a KUKA robot, and we have these biologically inspired robots that we like to send out into the field. But the truth is, we kind of program these biologically inspired robots as if they're industrial robots. And we don't want to do that because in order to go through, especially a scene like this where everything is totally unmodeled, you can't plan very perfectly every path. You need some sort of compliance that's built into your system, just the same way when we walk, we don't figure out exactly where to place our foot down. We have an approximate idea, and we let the compliance of our muscles do the rest. So if you look at, again, this standard equation of motion, what we're going to do is we want to have some sort of compliant controller for each of our degrees of freedom, but we don't want to deal with 16 degrees of freedom at once. So what we do is we take recourse back to the geometric mechanics where we were able to come up with a nice low-dimensional representation of how to prescribe a gate. We substitute that into our admittance controller, and now we have an admittance controller that's servoing on the parameters of the gate instead of doing all these degrees of freedom. And you can see, in this example here, we were able to put this robot on a pile of rocks. It doesn't know what the rocks are. We give it a nominal gate to follow, and now, in order to adapt for these vertical imperfections, it's running an admittance controller in the parameters that describe the gate, of which there's only two, because we like two-dimensional basis functions. It's worth noting that in our work with Dan, we were able to kind of characterize two kinds of snakes. It turns out that there are some snakes which are specialists, and there are other snakes which are generalists. So in my view of the world, the specialists are those old kinematic robots that we were talking about. The snake, it's just going to do the same thing no matter what environment it's in. Maybe it evolved some special capability for a particular environment. Take it out of that environment, it's not going to change its gait. Whereas the generalists, they're able to use this admittance controller, again, in my words, not what the biologist would say, in order to move through unmodeled terrains. So I should also, I want to point out that we've also taken the same gate design rules for legged systems, and we implemented this admittance controller again on one of these robots. Now, one thing I forgot to point out is that these joints here that you see, they are what's called a series elastic actuator. So what you have is this joint, a motor. On its output, there's a spring, and the output to the spring is the output to the system. If there's no load, everyone spins together. If there's some load, then there's a torsional deflection, and from that torsional deflection, you can infer how much torque is being exerted onto the mechanism. So we use that information to close the loop in the admittance controller, either for the snake or for this kind of robot. And then here, I'll skip this because we started using CPGs, and I don't want to talk about it. So the next thing that we're building is this, we're actually going to build a 6-foot-tall robot. This is the second version of it. It only has 3 legs. It's going to have 6 pretty soon. And the idea is here, can we use the compliance to damp out? Well, here we want to damp out compliance as opposed to use it for walking over spaces. Those modules that you saw in that robot, my students, we started this other company called Hebi Robotics, Japanese word for snake, and we focused on the modularity here. And one of the things we discovered about modularity is, yeah, we can build other kinds of robots, from snakes to the legged system and what have not. But the real discovery, at least what I found exciting, was that we're able to build good robots really fast. So here we built this robot arm, although not at the quality of an industrial robot, but we were able to build it in less than 25 minutes. So the idea is if you believe that the future of automation is mass production in quantities of one, low volume productions, if you want to be able to adapt your automation every day, you're going to have a system like this that will allow you to change and program, and I might add, customize your automation every day. This is Canada. There's a self-balancing robot, and Canadians don't say you're sorry when you bump into a robot. But it's nice that you can see there we built the self-balancing robot, granted on wheels, and again, that took us a week to build. This is one of my classes that I teach, and they have to program robot arms, and then the final programming assignment is they have to build these Jenga towers. And there's a lot of lessons that I was able to more effectively teach because we had access to these kinds of modules. The one up here is feeding people. There was a contest, you take a bunch of BBs and put it in someone's mouth. We didn't have it feed me or someone else little M&Ms because the students figured out very quickly, because time counts, they started doing things like this real fast, and I didn't want to get hurt. Okay, so let's talk about this last topic, then we'll finish up. So this is related to the multi-agent work that my group is doing. So we had this project with Boeing, and the idea is they want to be able to assemble planes. And the problem with assembling planes, you have to lay down a lot of fixed infrastructure. So they had this vision of, instead of taking the cost and the time to lay down fixed infrastructure, you can have magical mobile robots running around assembling things. So they came to us, and we were able to conceive of what these mobile mechanisms, these mobile manipulators should look like. So my group, we focused on the mechanism design aspect. But the other thing we focused on was the processes that you might be able to develop because you no longer have this traditional way of doing manufacturing. Can we change the manufacturing process? Now, one detail in all this, and we built the mobile robots, and this is just showing that we have nice modular mobile robots that drive away. But since I'm running out of time, I'm going to skip to this. What we have here, one of the problems, at least I found interesting, was multi-agent path planning. So the idea is you want to plan a path using, say, A star from start to goal. For one robot, it's yay hard. 2 robots, twice as hard. 3 robots, 8 times as hard. 4 robots, 16, et cetera. It grows exponentially. So what we did is we came up with a technique where if you let every robot plan for its own path and only locally construct your configuration space when robots come into proximity of each other, on average, you can beat this exponential growth. In fact, for this algorithm here, for this demonstration here, it's 200 robots going from start to goal. There isn't enough computation on the planet to plan one step into the path planner going forward, let alone be able to find the path. So we're proud of this result, and we have this other thing where teams get together to carry objects. It's actually easier because it's now 1 robot, not 3. And we're happy about this growth, but the truth is this is a centralized planner. And one of the things we want to do is try to get these robots so they can just fend for themselves without having to resort to know what everything is going on. So I know, for those of you who know me, or my inner Baichi is now mad, I don't know, we embraced reinforcement learning, okay? And with this reinforcement learning, these robots, they're trained, and now they can just look in a vicinity, once the policies are trained, they look in a vicinity of each other, and the right thing just happens because of this training. The thing is, we didn't just use, the truth is, what's the secret sauce? So the secret sauce, of course, is with reinforcement learning, you have to figure out the reward function. That's an art. But the other thing we did is we used only the reinforcement learning for 70% of the time. The other 30%, we used the original M-star algorithm to find paths. So sometimes people call this a learning from demonstration or learning from an expert, where in this case, the expert was the algorithm that we had developed before. So once we have this training, and then there's a neural net in here too that is computing the action to the state to action mapping. But what's pretty cool is now we can have like 1,000 robots all running around going from start to goal, and they have no knowledge of anything other than what they can see in their immediate vicinity. So they have a little window and they know what robots are there. And from that, the right things happen. The sad news is we haven't quite done well in highly cluttered spaces, and that's the thing that we're working on. And a fun thing we did is we used the same reinforcement learning. There's no M-star here, and we're able to construct towers without any, again, centralization. The only thing that I think is pretty cool about this particular example is if you'll notice, scaffolding is being created and being taken apart on their own. In other words, we're not telling the agents to build the scaffold, it just happens. What time do I have until?
You've got like 10, 15 minutes.
All right, perfect. I just want to point out a project that I'm doing with Nabil Saman, and I don't have the slide for that. I'll finish here. So I just want to summarize and then have time for questions. What I presented, is some of the things that are going on in my research group. Locomotion and how we might be able to reduce locomotion problems, something that's low dimensional from which we can start to do analysis, or at the very, very least get our first cut understanding as to what's going on. The path planning, that work was the multi-agent work. But what I have called ergodic coverage there, that was the where to palpate next. And for that, we're extending that to other problems. Design, and of course, closing the loop. So these are the 4 big areas that my research group works on. But I should acknowledge that we professors, we have a mandate. And each of our mandates are different. I think we'd all agree that research and education are part of it. But in addition to that, what's also important to me is democratizing capabilities. So for example, with the medical robots, the first-in-human operation that you saw, that was done by a cardiologist, not by a cardiac surgeon. So maybe right now you may think, oh, what's the big deal? But he was the first cardiologist to do an epicardial mapping of the human heart in a live person. So what we want to do is offload the burden on surgeons and allow non-surgeons to do more of these tasks. And this is a trend that's already happening. So for example, if 40 years ago, if your insides hurt a lot, eventually they would cut you open, they'd see you have inflammation, they'd say you have colitis, here's your prednisone, go off and have a nice day. Today, you get a colonoscopy. And the colonoscope is not done by a surgeon. In fact, a medical student can do it. Okay? That's the trend that at least I see with surgical robotics, with surgery in general. Procedures that used to be surgical being done by non-surgeons. In fact, one of the things I want to work on is called natural orifice transluminal surgery. That's when you enter the mouth, poke a hole in the stomach, and then remove the appendix, let's say. And what'll be nice about that is now you can do surgeries in offices. And in fact, you may be able to do some procedures out in the field, which may be important either in search and rescue or in battle. Likewise, with manufacturing, Mark referred to this Advanced Robotics for Manufacturing Institute. One of the things we want to do is lower the barriers so small companies can embrace manufacturing technology. Right now, they can't, and that's a big deal because 98.5% of all manufacturing companies in our country, are small companies, 500 or fewer people. Finally, entrepreneurship is something that's important to me as well. There's 2 reasons. One is, I want to empower students so they can, go get a kind of job that they can design for themselves. The other thing is I think we all agree, we want to see our research have an impact. And one way for that impact to occur is through having the students start companies and then continuing on with their research as they become products. So with this, I just want to once again thank you. I also have to acknowledge I've been very lucky to have had a lot of people in my career influence my thinking. Certainly the geometric mechanics came from Jim and Greg and Hirose. Mark gave us, for locomotion, Mark really gave me a lot of insight for snake robots. In fact, he was kind enough to lend me his models early on, with which we built lots of snake robots. Joel Burdick, I can't deny, has had a great impact, Andrew Lewis. And then Dan, of course, the snakes. And then the clinical collaborators, as well as some other Penn faculty. Dan has had impact in thinking about how the sensing planning loop should go for me, and VJ with the multi-agent system, especially with swarms. So I'll stop there and thank you for your kind attention and take questions.
We've got lots of time for questions. Let me start one. For a non-medical person, can you describe what was going on with the robot in the woman's heart? What was the robot actually doing?
Okay, so in that picture, if we go back in time, all the way back in time, she had what was called an arrhythmia. And an arrhythmia means that your heart is not beating properly. It's going at the wrong pace. And the reason why that's a problem is blood will then start to pool in your heart and clots will form. So you really want your heart to beat at the right rate. You don't want to get a sternotomy. So with an arrhythmia, so the first thing you try is you enter for the ephemeral vein, you go up into the heart, and then from the inside of the heart, you start to do what's called an ablation. So the reason why you want to do an ablation is that your heart is not only a muscle, it's a conductor. And sometimes if you can electrically isolate the 4 pulmonary veins that surround the heart, for whatever reason, you do that, and then the heart starts beating right. How they discover that, I don't know. So what they do with people whose hearts are in arrhythmia is you enter through the ephemeral vein, you go up and you start burning from the inside in hopes of forming these lesions to electrically isolate the 4 pulmonary veins. The problem is it's the outside of the heart that you want to burn, so when you're on the inside, you're just approximating. You're not really getting the burn. So that's unfortunate. 50% of these cases have to be redone. And then the next problem is 2% of the time, you actually accidentally kill the person because you form a clot in the burning and then he dies. This woman here had multiple intracardiac interventions, and nothing was working. So what we did is so she volunteered to get the ablation done from the outside. Now with her, in this case here, we still didn't know where the electrical connection was not working. So the first thing we had to do was do an epicardial mapping where we take this probe and we poke all these points on her heart to get an electrical map of the heart. Now that's something you couldn't have done inside. It has to be done from the outside. And when people have to get this procedure done, they break the chest, they crack you open, and they start poking. With that in mind, they then know where the problem is, where they see electrical activity not performing the way they should, and then they ablate around there. In this case here, we localized where the problem was, and in this case, it's a little unfortunate for us, or for her too, that her problem was on her ventricles. We were hoping her problem was going to be on the atria, because on the atria, if you just start ablating, everything is good. On the ventricles, if you want to do this ablation, you have to inject some medicine into the heart to accelerate it, so it beats really fast, and while it's beating fast, you do the ablation. And about 20% of the population can't receive this medicine, and she was one of them. So it's kind of her fault we didn't cure her. But we localized her problem, and she was able to get medicines, and I don't know what her status is now. For the other 2, we were able to do the ablation for the 3 in humans. I should also acknowledge that this robot's operated for ear, nose, and throat operations on 1,000 people, a little over 1,000. And you're probably wondering, why did we go from the heart to the in the mouth? And the reason for that was it had to do with a law that the FDA changed. And I don't want to get into the details of that law, but I'm happy to discuss it afterwards, at least my understanding of it. And because of that, this became an easier procedure with which we can get an indication. What's ironic is when we started the company, we were at our first board meeting, we made a joke. Hey, we should just call it cure sleep apnea and call it a day. Forget about the heart. And we laughed it off, and off we went. And now we're taking cancer off of people's epiglottises. So that's why we went to this. And now we have the indication to go colorectal surgery as well as belly surgery. Yeah, question, yes?
Inside the human body, is this robot navigating autonomously, or is that teleop?
Yeah, so for that, it's teleop, okay? However, one little story. Once, the video with the snake robot in the heart, what happened there is our doctor left the room, so it's just me and my grad students operating on the pig, and the IRB police came through. So my student hit a button and stepped back. And it actually it got to the destination, not the way we intended, but it got to the back of the heart where it was supposed to be. And that's a credit to his localization procedure. But the FDA is very, very skittish on the term autonomy. Okay? In fact, the reason why our robot was the first to be clear with the term robot was because we were able to convince them that robot doesn't equal autonomy. But right now, everything is teleoperated.
Have you considered how the robot propels itself against the tissue? Clearly, you're operating it.
Yeah. So I wish I can tell you, well, we just drove around the heart. It's like flying an airplane. But really, what we did is we loosened the robot a little bit, and we just went straight. And the compliance works out that you can go around the heart. Yeah, thank you. Any questions?
So, following off that, how much control do you actually have in the robot when you're not inside the person? How actually is it?
So, that robot, that particular robot, it's funny, Eskimos have this phrase, there's 28 kinds of snow, and to us it's a snow and slush. So a snake robot, it's like, there's no one snake robot, there's 28 of them. But for that particular robot, it can cantilever about either 60 or 80 centimeters, I'm forgetting which. And it can, it can make 1 turn, 2 turns, maybe a 3rd turn. And then beyond that, we have problems. The reason why we're curious about that length is we want to do natural orifice surgery with the guarantee we can hold it up. Thank you. There was a question over here? Yes.
Yeah, so you had this slide about the generalist and the specialist. And can you talk more about what distinguishes the two? And then my other question is, you have this goal of trying to capture these complex motions through basic states. Can you do that with a generalist, or is that possible?
Okay, so a couple things. I overstated something, I apologize. It's not my goal to represent things with 2 basis functions, with 2 variables. That's not my goal. It's my first step. And I think it's a great first step because it gives us, my colleagues, they want to model all the degrees of freedom, know everything at once, and I think that's too much. If we can start with some simpler models, let's see how much we can understand and learn with simpler models. And then once we feel we've exhausted that, then we'll start doing something more complex. Maybe add a 3rd basis function. Or actually, I'm envisioning that we'll have a hierarchy of these basis functions for different things. So that's the first thing. So I do believe there's more. In terms of the compliant control, what we do is we have this snake that assumes a nominal gait, okay? And then those series elastic actuators that can sense force, as they're sensing more and more force, that closes a loop with what I call an admittance controller. But instead of closing the loop on each of the joints, we're closing the loop on the 2 parameters that are in front of the basis functions. So in other words, it's not, turn this joint until you're nice and soft, turn this joint until you're nice and soft, and so forth. It's turn these basis numbers until you're nice and soft. And we've demonstrated at first that we can get away with just 2 of these basis functions. But I agree, I believe we'll have to do more as we go. But I'm not ready for that yet. In terms of the difference between the generalists and the specialists, they're going to invoke their gait. Okay, so it's pretty funny. There's some of these sidewinders. If you put them on a whiteboard, they're not going to go at all. Okay, if you take them out of their environment, they just waggle in place like a cockroach upside down. Do you have those here? Yeah. Yeah. That was sarcasm. But the generalists, what they do is they know how to reach out and push off of whatever vertical imperfections in the environment, whatever advantage they can get in order to push themselves forward. And I'm modeling it with those 2 basic, an admittance controller on those 2 basis functions. Thank you. Dan.
You've given us roughly 4 components of the work that you're doing. You've shown us at least 4 different, marvelously rich and distinct application domains. I'm wondering if you think that that you're doing 16 different things or 20 different, or do you think that there's a discipline of robotics that you're applying that you can articulate, or is it really applying many, many, many different design ideas, control ideas, and signal processing ideas in distinct settings?
Yeah. So.